along with this video, you will first want to download the Lecture 2 script from Canvas. Once you have it downloaded, you'll want to open it in RStudio. So as a reminder, there's two different ways that we can open files in RStudio. We could come up here to File, and we could click on Open File, and then navigate through the computer to wherever you have the file stored. Or over here on the right hand side, we could click on the three horizontal dots, and this will navigate through your computer. Now, one thing to remember though is that this is only going to show folders, it's not going to show files. And so as you click through here, if you don't see your files, again, not a big deal, they're not going to be there. Click open, and then the actual files will appear down here. And then we can click on the file and open the file. All right, so to get started, I'm going to make this just a little bit bigger. So what we've got here is our Module 2 lecture. So as a reminder, I always like to start my scripts with some comments up at the top just to remind myself what I'm using this script for. I usually put my name and my date up here. So in this lecture, we're going to focus on different data types in R. So some data types in R include vectors, matrices, and arrays. We're going to cover all of those today, as well as logical. Logical is essentially true or false. There are also lists and factors. We'll look at both of those later. And then previously, we already saw characters and strings, as well as data frames. So some helpful functions when dealing with different and possibly unknown data types are the following. To illustrate these, we're going to first define an object, and I'm just going to call it object and set it equal to the number 1. Remember, to run this code, I can either highlight it and click run, or if I'm just running a single line at a time, I can always just have my cursor on that line and click run as well. So to explore this object, what we're going to first do is look at the length. So the length of the object will tell us the number of elements or components. str is the structure function. It will tell us the structure of an object. And so here it is numeric and it has length 1. Could tell us the class of an object. This one is numeric. And it could also tell us the names. And notice in this case the names are null because this object doesn't have names. And we're going to talk about null here in just a moment. But let's just look at some other examples. So I could have object 2, and object 2, I'm going to make the vector 1, 2, and 3. So let's first run this. We can see that it's numeric and it contains 1 through 3. If I wanted to just look at object by itself and have that populate into the console, I could type object 2 and run that line, and I see it's 1, 2, 3. We could look at the length of object 2, and we see its length is 3. We could look at the structure, and one thing that's nice is you'll notice as I'm typing, our Studio is trying to auto-populate some code for me based on things that I've done recently. And so here I want object 2, so I could always just autofill that way. And we see its structure, it is numeric, contains the numbers 1, 2, and 3. Earlier I misspoke on the structure of just object by itself when I said that it was numeric and length 1. It's numeric and contains the number 1. And then we could also look at the class. And we see that this one is also numeric. So an example that might not be numeric, just to give you a third example here, is we could have a character vector. And so maybe this character vector is going to have the letters A, B, and C. And if we were to look at the class of object 3, we would see that it is a character. All right, so let's go back to the null that we saw earlier. And so it's important to understand the difference between 0, null, and NaN. So 0 is the numeric value 0. and so you can perform numeric operations with it. So you can do things like 1 plus 0 is equal to 1. Null is a non-numeric value, and we can think of it as just a placeholder. And so in this particular case, when we got null for the names, the reason that we got a null back was because that particular object could have had names, but it didn't. We didn't assign any names to it. And we'll talk about names more later on, but that's why it produced a null. NA explains that data is just missing for unknown reasons, and we'll work a lot with NA in the future when we work with missing data. NaN stands for not a number, and it is a numeric data type value representing an undefined or unrepresentable value. And so we're going to illustrate the difference between these. And how we're going to do that is we're going to create a vector that contains the numbers 0, 1, and 2. And then what we're going to do is we're going to replace 0 with some different options. So first we're going to find the mean of the vector containing 0, 1, and 2. And so remember that 0 is an actual numeric value, and so to find the mean of 0, 1, and 2, I would add up 0 plus 1 plus 2 is 3, and then divide by 3, and that's where we get the 1. So instead of 0, let's place a null in there. And remember that null is a placeholder. So since there's no value here and it's just a placeholder, when we use the mean function, what we're actually doing is just finding the mean of the numbers 1 and 2. What happens if instead of 0 we placed a character? Well, here we get that the argument is not numeric or logical, returning NA. And the reason for that is remember whenever we create a vector, and we're going to see this later on, but here since we have a character, what happens is that the 1 and the 2 are also converted to characters, so we can't actually find the mean of this, so it is just missing, so you have the NA. What if instead of a character we had placed an NA? In this case, we're still going to get that the mean is NA, and that is because we have a piece of missing information. So R says, you've given me a vector with 3 spaces in it and told me that one of the values is missing. So since that value is missing, there's no way for me to calculate the mean of those 3. And then finally, if we replace it with NaN, here we're going to get NaN back, and the reason for that is NaN stands for not a number. So if we try to take the mean of 3 things and one of them is not a number, well, we can't get a numeric value back. Alright, so we're next going to look at vectors. And so a vector is one of the most basic data structures in R, and it has to contain elements of the same type. And so there's different types of elements that we could place in there. We could have logical, which are the elements that are either going to be like a true or a false or a missing. It could be an integer, so think like whole numbers. It could also be what's called double, and it ends up, it's a historical anomaly that R has 2 names for its floating point vectors, double and numeric. Formerly it had real, and you can read more about that here. That's going a little bit into the weeds for this particular class, so I'm just going to kind of leave that there. But just know that this is another way for you to store numbers. You could have a character, which we've seen before. You can also have complex numbers, and then you could have raw, which again, this is more getting into the computer science side of things, but that's a raw vector that's used to represent a raw sequence of bytes. And so I have these all listed here for completeness, but know that we are primarily going to be working with numeric and character values in this course. So a vector's type can be checked with the type of function. And again, we're not going to spend too much time talking about these different types because a deeper discussion would be better suited for a computer science course or an advanced R course. So let's start out by creating some different vectors and see what these look like. So we're going to create a vector and we're going to name it y, and we're going to use that C function again. Remember that a C function is basically going to combine everything together that we have inside of those parentheses, and it is going to create a vector for us. So we could run this line of code. Notice that y now appears here in my global environment. If I wanted to display that vector, I could also just type the name of it, y, and run that line of code by itself. Alternatively, if I also wanted to display y in the console while I'm creating it, I could place an open and close parentheses around the entire thing. We can call different elements of y, and we can do this using square brackets. So y followed by squared brackets with a 2 in the middle will display the second element of y. If instead we had placed a 4 here, this would display the fourth element of y. And again, the type of function can be used to see what type of vector we have, and here we have a double, and so remember that is a numeric type. Now on the other hand, what if we have a mixture of numbers and characters when we try to create a vector? So here we're going to create a vector x and comprise it of 1, 2, the word 3, the word 4, and 5. Again, printing x down in the console. Notice that those numbers now have quotations around them. And the reason for that is if we come back up here, vectors can only have one type in them. So they can either have characters or they can have numbers. They can't have both. And so what happens when characters are placed inside of the vectors, any numbers are coerced to be characters. And so notice that these numbers down here have quotations around them. And if we check the type of vector for x, we can see that this is a character. And so you might say, well, why is this really important from a data analysis standpoint? Well, the reason for this is when we read in data, we need to be very careful. We might have a particular variable that really should be numeric, but maybe someone accidentally placed a word or a character or something in there, and when we upload it or when we read it into R, those numbers could be coerced to characters, and so that can create errors. And so this is why you just want to be aware of, keeping in mind that if something like that happens, we might need to change something so that we actually read that in appropriately. We can explore lots and lots of attributes of vectors. I'm not going to go through all of these in the video, but I do, suggest that you go through these on your own. We already saw that we could return elements of the vectors. We could also return everything except certain elements. And so if you place a negative sign in front, it will return everything except for the first element. We've seen the length function in the past. Remember that we can always assign lengths or any other functions to be equal to an object, and so that can become useful. We could look at the sum, mean, variance, standard deviation of y. We could take the square root of the variance to get the standard deviation. Min, max, range, we can sort, we can reverse, we can create a table, and we could even create relative frequency tables by dividing by length. So play around with these on your own. Remember that y is this vector right here. So while you're learning, it's always a good idea to kind of test to see if the output you get is what you would expect. So for example, put these numbers into a calculator and see if you get the same mean that R produces. Or write down by hand, okay, what would this look like if I reverse that vector? Do I get that vector when I run the reverse line of code in R? It's always good when you're coding to try to build intuition. We never want to blindly trust whatever R is giving us, and that's because we could always have mistakes in our code. So whenever I'm running code, I'm constantly doing, just even small sanity checks to make sure, okay, does this output look like I think it should? Okay. We can also find elements of a vector having certain characteristics using the which function. And so the which function can be really useful for finding different elements. Whenever people generally use the which function for the first time, it can be a little bit confusing, so give it some time. Don't expect to get it, right off the bat, but it is very useful. And so I'm going to do an illustration of that here. So we're going to start out again with that vector y. So just to remind ourselves, I'm just going to highlight the letter y. I'm going to run it so that y is produced down here. So suppose that I'm interested in the elements of y that are greater than 20. So looking at my vector down here, notice that the fourth element is greater than 20, the fifth element, the sixth element, and the seventh element. All of those are greater than 20. And so essentially what I'm trying to do is I'm going to try to write some code that can pull those values out for me. So the first thing I could do is create a logical vector. And to do this, what I'm going to ask R is I'm going to say, okay, take the letter y, which is my object here, greater than 20, and let's see what this returns. So notice it's going to return a string of trues or falses, and essentially it's going to go through and it's going to check which of these are greater than 0, or greater than 20, and which of them are not. So notice that the first 3 were not greater than 20, but the last 4 were. So now let's place that argument inside of the which function and see what it returns. So notice that the which function is going to return 4, 5, 6, and 7. And this is because the which function returns the indices of the vector which satisfy whatever the argument is. So in this case, we were looking for the values of y which were greater than 20. And so the which function is going to return 4, 5, 6, and 7 because the 4th, 5th, 6th, and 7th elements were the ones that were greater than 20. So I could assign an object to be greater than 20, which is going to store the indices of y which are greater than 20. And so notice greater than 20 is equal to the 4th, the 5th, the 6th, and the 7th. So now if I want to pull out those elements of y which are greater than 20, what I can do is use that square bracket notation we saw earlier. And what I'm going to do is inside of those square brackets, I'm going to put that object greater than 20 because again, remember that greater than 20 is the indices of y which are greater than 20. And so notice this is going to produce that 4th, 5th, 6th, and 7th element of y. And then I could assign this to be a new vector. I'm going to call it new y. And notice new y only contains those elements of y which were greater than 20. Now in order for this to work, you'll notice that I used a logical operator, and that is the greater than sign. There are lots and lots of useful logical operators. So here are those operators. Now one thing to notice here is the colon is not part of the operator. The colon I've just put there to say, hey, this element gives you this. So a double equal sign gives you equal to. We have the greater than sign, greater than or equal, less than or equal to. The exclamation point in R is the negation sign, so it means not something. So for example, if you had exclamation equal, this would mean I want y not equal to 2. The and sign is the and symbol, and it means and. I should delete out these dollar signs. We don't need those there. And then the vertical bar, that is the or symbol. So actually I need to take all those out. So the and sign, this will be fixed in your script, you'll see this. The and sign means and. And then again the vertical bar is the or sign. So one useful method for summarizing a vector, so we're going to switch gears here just a little bit, is to use the table function. And so I've got a line of code here. What this is going to do is this is going to generate some random numbers for me. I just needed something to generate a bunch of numbers so you can see what the table function looks like. So here we're going to take a random sample from what's called a binomial distribution. If you're not sure what that is perfectly fine. Honestly, you can think of this as I'm going to flip a coin, is really what this is doing. And what it's saying is I'm going to flip a coin 1,000 times. I'm going to flip a coin 10 times, and I'm going to repeat that 10,000 times. And my probability of seeing a heads on my coin flip is 1/2. So just to repeat that, I've got a fair coin. I'm going to flip that coin 10 times. I'm going to record how many times I see a heads, and I'm going to repeat that 10,000 times. And what you're going to see, and we can see this up here, is random binomial, this object contains 10,000 numbers. So it's a vector that's 10,000 long. So if I try to just print this out in R, I'm going to get a whole bunch of numbers here. And in fact, R is going to say there's too many for me to even print here. So a useful way to summarize that is using the table function. And so here is a table. So notice out of my 10,000 trials, There were 8 of them where when I flipped the coin 10 times I got 0 heads. There were 10 of them where I got 9 heads. There were 2,402 of those where I got 5 heads, and so on. So if you have large vectors, the table function is very useful to summarize those vectors. Now, do keep in mind, if that vector is comprised of numbers that have decimal places or that where they're all unique, the table function really isn't going to do anything for you. It's really useful when either you have a character vector where it takes few options, or you can have numeric where it also takes few options. All right, next we're going to look at matrices and arrays. So a loose definition of a vector is a one-dimensional array of data. A loose definition of a matrix is a two-dimensional array of data. And so in R, we can specify an array, it ends up of any dimension up to a certain point, although vectors and matrices are treated as separate cases. So let's start out by creating a matrix. So in order to create a matrix, one way that we could do that is we could create a blank matrix and then we could fill in the elements. So I'm going to create a blank matrix using this line of code. So the object A is going to be equal to a matrix filled with NAs that has 3 rows and 2 columns. So let's run this and then let's look at what A looks like. So I'm going to print A down below. So notice that we have 2 columns, we have 3 rows, and that each of them is filled with a missingness or missing value. So next what we can do is we could go in and systematically fill these in. So when we call A1, 1, what this is going to do is this is going to call the element in the first row and the first column, and we're going to set it equal to 3. So let's run this, and now let's call A again. So notice the element in the first row and the first column has been replaced with a 3. We could next replace the element in the first row and the second column with 8. And so again, looking at A, we now see in the first row and the second column we have an 8. And then we could fill in the rest of them, and we see that that matrix is now filled in. Now you can imagine if you had a big matrix, this would take forever. It's not, probably the best way to do this. So let's look at some other options. So another approach would be, instead of using NAs here, we could put in a vector that has all of the numbers that we want. And so here you'll notice I've got a vector with 3, 4, 1, 8, 6, and 7. That's the numbers that's in this matrix here. So let's run this and see what matrix B is going to look like. So notice B is the same as A. So let's talk about how R uses that vector to fill in the matrix. So notice in the vector we have 3, 4, 1, 8, 6, 7. And if we go down the rows, we have 3, 4, 1, 8, 6, 7. So by default, R is going to fill the matrix by going down the I said rows a minute ago, I meant columns, by filling it in the columns one at a time. So we're going to start at column 1, fill in the numbers. When we run out of space, we move over to column 2. Instead, we may want R to fill it in row-wise. To fill it in row-wise, we can add in the by row equals true. Now notice if we're going to do this, we have to change the order of the numbers in the vector, because now we want it to go through the rows. So we want it to go 3, 8, 4, 6, 1, 7. So running this and now checking the matrix C, notice that all 3 of those matrices A, B, and C are the same. Another way that we could create a matrix is we could define separate vectors and then combine those vectors together. So for example, I could create the vector, and I'm going to call it row 1 and set it equal to the numbers 1 through 10, and row 2 and set it equal to the numbers 11 through 20. So if I wanted to combine these into a vector, I could use either the rbind or the cbind function. So rbind is going to bind them by rows. So before we do this, let's actually run row 1 and row 2, so we have them here so we can see what they look like. If we use the rbind function, notice it's going to combine them by rows. So 1 through 10 becomes the first row, 11 through 20 becomes the second row. If we use the column bind function, notice that row 1 becomes the first column and row 2 becomes the second column. We can perform different operations on matrices. So if you haven't had a linear algebra course and you're not familiar with these matrix operations, that is not a big deal, but just to show you a couple in case you are, you could find the transpose of a matrix, you could add matrices, and you can even do matrix multiplication. We can also perform functions on matrices using the apply function. So the applied function is a really useful function if we want to perform operations either row-wise or column-wise in a matrix. So recall matrix B. So I'm just going to run it down below. Here's our matrix B. Suppose we wanted to take the sum of the rows. So in other words, we want to add up each of the rows in matrix B. Well, what we can do is in the apply function, we'll place matrix B. Next, you're either going to place the number 1 or the number 2. If you place the number 1, it's going to perform the operations by row. If you place the number 2, it's going to do the operations by column. And then you just tell it the name of the function that you want to apply to each of those rows. So running this one, notice that we get the sum of each of the rows. So 3 plus 8 is 11, 4 plus 6 is 10, 1 plus 7 is 8. If we change this to a 2, it will do the same thing but by column. So notice the sum of 3, 4, and 1 is 8, and 8, 6, and 7 is 21. Another example here would be if we wanted to find the median of the numbers. Alright, so let's look at one more example here. We're going to look at a simulated example. So what we're going to do is we can actually name the columns and rows of a matrix. So at first the matrix will have the numbers for the names of the rows and columns. For example, suppose there are 3 migraine drugs we wish to compare and we want to simulate data under the following conditions. So each drug will be tested during 4 trials, where each trial consists of 25 people. And it ends up that drug A reduces migraines 45% of the time, and drug B reduces migraines 50% of the time, and drug C reduces migraines 55% of the time. And so what we could do is we could simulate the number of people experiencing relief using the code that I've got down below. So we've got that R binom. So remember, that's kind of like flipping a coin. So here, since each of our trials are 25 people, we could think of that as flipping a coin and figuring out of those 25 which ones are going to receive migraine relief based on based on how well these drugs work using the numbers that we have up above. So to create my simulated data, I'm going to combine 3 different vectors. The first one, we're going to have 4 trials, each with 25 people, with probability of success 0.45. And that's because in the first drug, we reduce migraines 45% of the time. We're going to add on a second vector, which again, we're going to have 4 trials with 25 people, but this time the probability of relief is a half. And then in my third one, I've got 4 trials again, 25 people in each trial, with a probability of success of 55%. So here is my simulated data. And so again, if we look at this data, right now, without any names, it's kind of hard to see what's going on here. But what we've got is 3 different drugs and 4 different trials, each of the trials consisting of 25 people. So for drug A, in the first trial, 10 people felt better. And for drug A, in the second trial, 13 people felt better. But if we're going to create data like this, it would be really useful if we could name the rows and the columns to help us out. So let's see how we can do that. So I'm going to create a character vector with my drugs' names, drugs A, B, and C. And then I'm going to use the function column names to add those column names to my simulated data. So notice now my simulated data has drug A, B, and C. I could also add row names. So this one, what I want to do is have trial 1, 2, 3, and 4. So instead of column names, I'm going to add in row names, and I'm going to create my row names a little bit different than I did above. Now I could have done the same method I did here and created a vector that said trial 1, 2, 3, and 4, but I'm going to show you something a little bit fancier with the row names. So what I could do here is I could take my simulated data. I'm going to set do.null equals false, and I'm going to have a prefix dot trial. And so let's see what happens when I run this. Notice I get trial 1, 2, 3, and 4. So the trial dot, that prefix piece, that's here. But notice that for each of the rows, we've tacked on a 1, 2, a 3, or a 4. And so that's what this piece here is doing. All right, so an array can be specified in a similar way. And so remember, an array needs to not only have 2 dimensions. So now we're going to switch over to arrays, not just a 2-dimensional matrix. And so to illustrate this, I'm going to define an object temp equal to 1 through 8. So this is separate from the simulated data exercise up here. And then here I'm going to take G and make it an array using that vector temp with dimensions 2, 2, and 2. So notice this is a 3-dimensional object here. And so now we can think of this as a layered matrix. So we have a matrix and then another matrix on top of it. So one way to think of this would be almost think of like what a Rubik's Cube looks like, where each of those squares in a Rubik's Cube, that could be an element of the array in 3-dimensional space. Now, I will be honest with you, I'm showing you this for completeness. Majority of you will never have to work with arrays. Vectors and matrices will give you everything that you need. And notice we could check our data types here. So D was a matrix that we defined earlier. We could see that a matrix is both a matrix and an array, whereas G, the array that we just created, is an array and not a matrix. And then the last piece is we can manipulate different data types or coerce them to be different things. So here I'm going to define a vector X. I'm going to ask, is X a matrix? No. But is X a vector? Yes. But technically X could be a matrix. It would just be a matrix that would either have a single row or a single column, which is perfectly valid. So what we do is we could coerce it to be a matrix by using the as.matrix function. And so notice that now it's not a vector, it's a matrix with a single column and 4 rows. And so just a final caution here, sometimes R will not make a variable into a matrix even if we use the as.matrix. So always make sure to check that R has successfully changed the data type. And this goes for any type of coercion that you do. All right, so as always, if you have any questions, please let me know. Again, this is a lot of information. Just give yourself some leniency as you're learning R coding. It has a very steep learning curve. So really the goal is just to pick up these pieces as you go, and then eventually you're going to see how all these pieces kind of come together. But again, it does have a steep learning curve, so make sure you're giving yourself some grace. Don't get too frustrated. You'll ask lots of questions when you're getting errors, and just know that I'm here to help you. And I also encourage you to help each other. Use that discussion board as you need to. So have a great day, and if you have any questions, let me know.